Hello everyone, welcome to the biggest ideas in the universe. I'm your host, Sean Carroll. And last time when we talked about scale, we had the pleasurable experience of going back to the real tangible world just a little bit, being a little bit more down to earth after several lectures on quantum field theory. We're going to get abstract again over this lecture and the next one, but it's in a slightly different direction. We're going to be thinking classically again. What we're going to be doing is laying some of the mathematical groundwork for the lectures to come. I keep saying lectures. The videos, the ideas to come. We have big ideas. They're going to require a tiny bit more mathematical sophistication, but it's more conceptual, less algebraic and equation-based, so I think it will be okay, but I'm going to be giving away some of the ideas that we physicists use all the time and we don't usually talk about in popular level treatments of the subject. So today, we're going to be talking about geometry and topology. You will notice these are two different ideas, and they're not really physics ideas. They're completely mathematical ideas. So, of course, they each are huge subjects which deserve videos of their own. They're not going to get them. I'm going to try to squeeze both of them into a single video, and I'm going to be concentrating specifically on very specific aspects of geometry and topology, ones that will be relevant to what we're going to be talking about coming up. So it's not going to be covering the whole field. So think about geometry and what do I mean? What I mean is non-Euclidean geometry. So to make sense of that, let me first talk about Euclidean geometry. This is the geometry that you learned in high school or wherever you learned it. Even if you didn't take any formal courses in it, you've heard about Euclidean geometry. It's the geometry of tabletops. It is sometimes literally called tabletop geometry. It's the geometry of flat planes and flat three-dimensional surfaces. So Euclidean geometry is things like if you take a triangle and you add up the angles inside, they add up to 180 degrees. Sometimes 180 degrees is called pi radians. Just as a little math fact there. But we can use degrees. We're not going to be trying to be too snooty here. That's one fact about Euclidean geometry. Here's another fact. The parallel postulate, which is an interesting, has an interesting status, let's say, in Euclidean geometry. The parallel postulate says the same thing. Imagine you have two lines going off at right angles to a common line. So I'm thinking of these two lines going horizontally across the page. The parallel postulate essentially says, there's different formulations of it, but essentially says that you continue these lines forever and they remain exactly parallel. They remain exactly the same distance apart from each other if they start going in the same direction and at right angles to each other, okay? This is, I think, the fifth of Euclid's postulates, and it's one that sort of seems more specific than the other ones. The other ones of Euclid's postulates, Euclid was a real person in ancient Greece, who came up with this formalization of geometry. He had help, but we give him credit these days. And the other postulates are more or less self-evident, like, it's sort of what you mean by a point and a line and things like that. Whereas this one, I don't know, seems a little optional. And there's been for a long time this idea that maybe we should be able to derive the parallel postulate from other postulates. And in fact, when I took geometry for the first time in junior high school, our teacher gave us an extra credit assignment of junior high school? No, high school, I guess. He said if you can prove the parallel postulate from Euclid's other postulates, or the other postulates that we had in the class, then he would give us extra credit. I was ignorant enough to actually try to do it, but I was not stupid enough to succeed in doing it, because you can't succeed in doing it. That's the point. The point about the parallel postulate, it is independent of the other axioms. That's why it's a good axiom. If it were provable from the other axioms, you could remove it from the list of axioms. And one of the reflections of the fact that it is removable is that you can contradict it. You can have other postulates that say other things, and that's the birth of non-Euclidean geometry. So Euclidean geometry, of course, works for triangles, works for straight lines, but it works for a whole bunch of things. I mean, there's a whole huge subject of Euclidean geometry about conic sections and inscribing circles within squares and calculating areas of things. I'm not going to be talking about any of that stuff. I want to dive right into what happens if we violate the parallel postulate, if we replace it with something else. So there are basically two choices if you want to violate the parallel postulate, right? Or if you want to replace it with something else. You might say that, well, maybe parallel lines generally focus on each other. If you start off with two parallel lines, that is to say lines that are both moving at right angles to some common line segment, maybe over space, as you extend them out, they come closer and closer and eventually cross. That is something that could happen. It does not happen in Euclidean geometry, but you could imagine it happening. You could also imagine diverging. You could imagine starting with two parallel lines, moving at right angles to a common segment, and as they move off, they get further and further away. Both completely standard, or completely plausible, in other words. And what you could do is you could actually invent a rule for how quickly they focus in on each other or how quickly they diverge. And interestingly, this was first done, I think in the 1800s, by Lobachevsky. No chance I'm going to spell Lobachevsky correctly, because I don't even think it's standardized. And Bolyai. These are two... Oops, I should be able to spell his name correctly. They invented what is now called hyperbolic geometry. They worked independently from each other. Two mathematicians I'm not even going to get their countries right. I just don't know the history of this stuff nearly as well as I know the history of physics. But Lobachevsky and Bolyai both said, well, okay, what if we, in effect they said this, again, I never read their papers, but in effect what they said is, what if we examine this possibility that the lines diverge rather than remaining parallel? And they developed a set of rules for what is now called hyperbolic geometry in parallel. You can, just like you can prove that the angles in the Euclidean geometry have the angles in a triangle in Euclidean geometry add up to 180 degrees. In hyperbolic geometry, a triangle sort of looks more like this because lines diverge. And you can prove that the angles inside are always less than 180 degrees. How much less depends exactly on the triangle and exactly on the geometry, but it's consistently less than that. And this was interesting. It's not completely clear that Lobachevsky and Bolyai were the first to invent this. Gauss, Carl Friedrich Gauss, who was one of the greatest mathematicians of all time, he claimed to have done it first. Gauss, apparently, he was one of the greatest mathematicians. He could also be a bit of a dick, apparently. He was very fond of talking to other mathematicians and being told by the others, oh, I have some great new result. And Gauss would say, oh yeah, I had that several years ago. I just decided it wasn't worth publishing. So he did that exactly to non-Euclidean geometry. And usually, I think he was right most of the time. Like he didn't publish that much, but he had a huge number of results. And so Gauss thought about this, Lobachevsky and Bolyai thought about this, and there is a story that you are sometimes told in the popular physics literature that goes something like, Euclid invented Euclidean geometry, and then Lobachevsky and Bolyai invented non-Euclidean geometry, and that led right into general relativity, the curvature of space-time. So that's true, but it leaves out an enormous amount. And in fact, the specific work done by Lobachevsky and Bolyai in inventing hyperbolic geometry is not even specifically relevant. It's not very helpful, let's put it that way, to general relativity at all. It's far, far too specific. It's also like a little bit weird. In retrospect, it's a little bit weird because think about a surface on which you could actually use hyperbolic geometry. Like when I'm trying to explain non-Euclidean geometry, the most obvious thing in the world is to look at the surface of a sphere, okay? Here's a sphere. And you can take a little line segment being, for example, on the equator of the sphere, and you can shoot two parallel lines up, and guess what's going to happen? They're going to come together at the North Pole or the South Pole. So that's an example of this focusing kind of geometry, not this diverging kind of geometry. So this is, this spherical geometry is very visualizable, whereas if you actually want to get hyperbolic geometry, people say it's sort of saddle-shaped and things like that. So you can draw a saddle, and you can sort of put a point there and have two lines that are initially parallel, and they will diverge from each other. Da, 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 da. So a saddle shape, or a Pringle, if you're a fan of the American potato chips, saddle or Pringle-shaped geometries are hyperbolic. But there's something nicer about the sphere than the saddle, which is I can embed the entire two-dimensional sphere perfectly accurately inside our good old three-dimensional space. Whereas this saddle is indeed curved in the sense of Lobachevsky and Bolyai, but it's not constant curvature. They were actually examining the very, very specific case where the curvature was exactly the same in all senses and in all places in your geometry. That's true for the sphere. The sphere is completely symmetric. Its amount of curvature is the same everywhere. there exists a hypothetical two-dimensional geometry, a negatively curved hyperbolic geometry, for which that's true in the diverging sense. But the saddle does not quite fit that category, that criterion of being constant curvature everywhere in the form in which it's embedded in our three-dimensional space. So that's a long-winded way of saying it's actually hard to visualize absolutely symmetric, constant curvature, hyperbolic geometries compared to spherical geometries. But nevertheless, historically, that's what they did. They invented the negatively curved. This is, just to make this clear, this is called negatively curved geometry. Sphere would be positively curved. And Euclidean would be flat. Zero curvature, okay? Euclidean geometry. And all these are possible. So it's perfectly allowed to invent hyperbolic geometry first as an alternative to Euclidean geometry, but it's just weird to me that they didn't invent spherical geometry first. However, like I'm hinting at, none of these is what we want in some sense. I mean, these are all a starting point, but a very, very tiny starting point. We need to work a lot harder to get what you actually need for physics out of this. So it was Gauss who first sort of figured out how to do something more general. And what I mean by more general is, let's imagine that instead of generalizing a flat Euclidean plane, 2 dimensions, instead of generalizing it to a two-dimensional sphere or a two-dimensional saddle, we just let it be any old thing, okay? We just let it be some wildly diverged thing. There's sort of all lumps here and whatever. It has curvature of arbitrary amounts in arbitrary directions everywhere throughout it, okay? That's really what you want. In general relativity, because we're going to get to general relativity eventually, and that says that space-time is curved. And if you ask yourself, well, is it positively curved or negatively curved? Well, in some places it's positively curved, in other places it's negatively curved. And in fact, you need a lot more information than just positive or negative to tell me how curved it is. That's what we're going to develop right here. And Gauss was the one who made the first steps toward this. He was examining surfaces, two-dimensional surfaces, and he figured out different ways to characterize the curvature at a surface. So for example, here's one way that you could do it. Take on a sphere, take the North Pole, and consider circles, lines of latitude, okay, around the sphere. Well, they would have, around the North Pole. So they would have a circumference, just like in this flat geometry, circles would have a circumference, okay? There's a radius and a circumference. And in flat geometries, the circumference is simply 2 pi times the radius, 2 pi r. That is how far you have to go around the circle. If you look at this spherical geometry over here, you notice that the circles are sort of moving toward each other a little bit compared to what they would be in the flat geometry. So if you try to calculate the circumference of a circle in the spherical geometry as a function of the radius, you find that consistently the circumference is, oops, that's exactly what I didn't want to write. The circumference is less than 2 pi r. Every single time for a circle. Whereas on this saddle over here, if I were to draw some circles and I were to compare it, it's hard to see on the thing I drew because it's hard to draw a negatively curved surface. But here the circumference is consistently greater than 2 pi r, where r is the radius of the circle. So that's one example of what I mean by characterizing quantitatively the curvature of a surface. Once you say that, once you say, well, okay, the circumference of a circle of fixed radius is not 2 pi r, it's something else, maybe what I can do is I can say, well, how different is it? How less is it? Of course, it's infinitesimally less, but then I can use calculus to sort of differentiate, take the derivative of how the circumference is changing as a function of the radius, and I could characterize that separately at every point. It's not once and for all a feature of the geometry, but at every point in space, I can draw a little circle, or if in three-dimensional space, a little sphere, and I can compare how the area of the sphere or the circumference of the circle would depend on the radius. Compare that to what it would in flat space to my curved geometry. And I can do that separately at every point. So I get a number at every point, which is how much I'm deviating from completely flat Euclidean geometry, and that number could be positive or negative. So that's an example of how you could characterize curvature locally. And it's clear just from sort of examples you could imagine in your head that a curved surface could be very curved some places, not so curved other places, so that's really what you want. And Gauss figured out how to do this for this case of two-dimensional surfaces. But then he noticed something, because he was one of the greatest mathematicians of all time. He noticed something. He noticed that there are ways of characterizing the curvature that don't make use of the fact that this two-dimensional curvy thing is embedded in flat three-dimensional space. So think about, there's sort of extrinsic. Sorry, my brain was thinking something else, so I wrote badly. Extrinsic versus intrinsic curvature. Extrinsic is just the curvature you get from looking at it from the outside, whereas the intrinsic curvature is what you get from looking at the inside. So if you have, let's say, this circle, and this is literally supposed to be a circle on a plane, okay, so it's a two-dimensional circle embedded in, sorry, a one-dimensional circle embedded in this two-dimensional plane, versus, let's say, this blobby thing, okay? So you would say, look, well, this one is curved, but kind of smooth, not that curved. This one is also curved, but it's curved in a different way everywhere. So what Gauss says is you're thinking extrinsically. You're thinking about how the thing looks from the point of view of the outside. But what I want to do, Gauss, is I want to think about what if I were a little person living in that surface, living on the surface of the circle. It's hard to imagine that, but I can imagine being a little person living on the surface of this two-dimensional plane, or I could imagine that three-dimensional space itself has curvature, and I could be a person living in that, right? So in that case, what Gauss shows is that this circle here and this circle-like thing that is kind of wobbly have exactly the same curvature. In fact, technically they have zero curvature, as we'll see in a second. But the point is that you're moving the circle in the place where it's living, but you're not changing its intrinsic geometry. So what Gauss figured out is what you really want to be able to do is two things. You want to characterize the geometry intrinsically to where you are. And number two, you want to be able to characterize all the different ways in which the surface or the volume or whatever you're in is curved. This fact that circles or spheres change their area or circumference differently as a function of the radius is one way, but there could be lots of different ways, lots of different aspects of curvature. And Gauss did not quite finish this project. He didn't quite tackle it all the way, but he had a very talented student named Bernard Riemann. Riemann was a brilliant mathematician who went on to do many great things. Riemann also died when he was 39 years old. So when you look at all of the things that Riemann accomplished, keep in mind that he didn't reach the age of 40 before he did those things. So Riemann apparently, he needed to write some thesis, some dissertation to get some job in Germany, and he went to Gauss and said, okay, here are the different topics that I'm thinking about. What's your advice? Which one should I do? And this is the story I'm told anyway. I'm not, again, don't know the history very well, but Gauss said, oh yes, this one, the foundations of geometry. Do that one. And apparently Riemann thought that was the most boring one that could be done, but he did it, and he invented what we now call Riemannian geometry. Pretty cool. And so what I want to do is give you some of the fundamental basic concepts of Riemannian geometry. Riemannian geometry is the answer to the question, if I have not just a two-dimensional surface, but any space of any number of dimensions, so three-dimensional space, four-dimensional space-time, whatever you want, and I curve it not just uniformly everywhere, but I curve it arbitrarily at any point, okay, in different ways, at different locations in space, and as we now know, in time. How do I completely characterize the amount of curvature? How do I know how curved it is? How do I describe that mathematically? So he figured out how to do this. And basically, I think that the thing to think about are straight lines. This is my favorite way of getting into Riemannian geometry. What do you mean by a straight line, right? Well, we have one notion of a straight line, is that the straight line is the shortest distance between 2 points, okay? That's perfectly good. So version 1 is shortest distance. And you can do that. You can generalize that Euclidean notion of I have 2 points and I take the shortest distance path. So in Euclidean space, I take 2 points, and I notice that this shortest distance path is straight. Other ones that are not straight will always have longer distance if I measure the distance along them. And I can do that equally well in a curved space. So what we call great circles on a sphere are lines that are as straight as they can possibly be. If I take a point that is here at the North Pole, and then take another point that is at the equator, and I connect them, there is This is part of a great circle. If I go all the way around, a great circle is just something that is like the equator, but it's not necessarily at the middle. It's anywhere oriented around the sphere. And this is the spherical generalization of the idea of a straight line. You can show that these great circles are the shortest distance between those 2 points. And then you can show other things, like if I do another point there, then the shortest distance here is along the equator. If I connect these, there's another shortest distance curve, another line of longitude in this case, and then I can add up the angles inside the triangle, and they're always greater than 180 degrees because it's a spherical geometry. I can do all that stuff, okay? So that is one version of what you mean by a straight line. How would you generalize this to a completely arbitrary geometry? Well, you remember when we did the principle of least action, we had this idea that there was some quantity, the action, that you could get by integrating over an entire path for a particle or for some more complicated physical system. And then the real path, the real trajectory that obeys the equations of motion, minimizes that action. So you can do exactly the same thing for the length of a curve. But what you need is a way to calculate the length, okay? So that's what Riemann figured out how to do. He invented something called the metric. The metric basically is the infinitesimal length. It's not quite the infinitesimal length. Again, this is one of those times when all of the experts in the audience are cringing a little bit, but just lighten up, guys. It is a way of calculating if I give you an arbitrary curve, and I want to take a little bit of it. Okay, there's a tiny little segment because I'm thinking like calculus, right? This is all what we call differential geometry. It's all calculus-based reasoning where you take infinitesimal things, figure out what's going on there, and then add them together along some finite-sized thing to get the final answer. So there's something that called Pythagoras' theorem, right? That you can take these, if you had ordinary Euclidean geometry, you would say that A, B, C, if A is the length of one of the ways you can go, B is the perpendicular way, and C is the hypotenuse, then A squared plus B squared equals C squared. So basically the metric is a generalization. Pythagoras' theorem, C squared equals A squared plus B squared. It says that C squared does not necessarily need to equal A squared plus B squared, but equals some function of A and B. In fact, it's some quadratic function. So it could be something times A squared plus something times B squared plus something times A times B. Okay? So 2 factors of A and B in general. So in fact, let's write it that way. So the infinitesimal length of this tiny little curve segment here equals something, call it alpha times A squared plus beta times B squared plus gamma times A times B, okay? So the numbers, alpha, beta, and gamma, are telling you how to calculate the length of an infinitesimal curve in an arbitrarily curved geometry. That's what the metric does. And then you can just add them all together along the curve. It's like a little odometer, right? You're pushing this little odometer and it's measuring your path length as you go. And these numbers, alpha, beta, gamma, that tell you how to convert little coordinates, which are what A and B are, into physical lengths, which is what C is, they could change from place to place in the manifold, as we call this space of all different points. A manifold, a space, whatever you want to call it, some curved object in geometry will in general have a metric that is different at every point in the manifold. I got to call it a manifold, sorry, that's what it is. So the manifold is this space that is curved. Whatever it is, how many ever dimensions. It could be, by the way, by is curved, I mean could potentially have curvature. Maybe it's flat, who knows? But it is the space that we will be talking about when we characterize what the curvature is, okay? The curvature of a manifold. So space-time is a manifold, a 4-dimensional manifold. Space that we live in is a 3-dimensional manifold. The tabletop is a 2-dimensional manifold. The sphere is a 2-dimensional manifold, and so on, okay? So the metric is, guess what? It's a field on the manifold. It's a kind of field that exists at every point, and at every point it answers the question, if I have a little straight line segment, how long is it? That's what the metric is. And I can add that up to get the length of a finite-sized curve. And that's a wonderful way to do it. That's a wonderful way to sort of generalize what you mean by a straight line. A straight line is the shortest distance path between 2 points. You can generalize that to arbitrarily curved surfaces. Riemann tells you how to do that. But there's another way of talking about a straight line. A straight line can be thought of as keep walking in the same direction. So if I'm literally on a flat plane and I'm just walking, right? If I were to wander around in different directions, what I would mean is that the momentum or the velocity or the little vector that points towards the direction I'm moving keeps changing around. Okay, like I move around and my velocity changes. That vector is sort of wobbling back and forth as I'm moving. Whereas in a straight line, I just keep walking in the same direction as the vector is pointing, as the velocity, as I have already been moving. If there's something that says, here's the direction I was moving in infinitesimally long ago, I will keep moving in that direction now. That is what I'm going to do. So in flat space, this idea, you are in flat space, you have a point here, you are initially walking in that direction, and you just keep walking in that direction until you reach some other point, you're going to end up moving in a straight line. Okay, that's what you're going to do. So that's an equally good alternative definition of what you mean by a straight line. Just keep walking in the same direction. That also works in these more complicated examples. If I start walking north from the North Pole and from the equator, and I just keep walking in the same direction, I will end up doing a great circle path until I reach the North Pole. Everything I just said goes through. So Riemann was smart enough, and again, I'm not even sure that it was Riemann who did this. He sort of got the answer, but I'm not quite sure what his reasoning was, so I shouldn't attribute it to him. But what we realize is that there's some notion of what do you mean by keep walking in the same direction, okay? You have this vector, and you're saying move in the direction of the vector. The vector is the thing that is pointing in the direction I have been moving in, and what I'm saying is keep moving in that direction. So what I need is a way to sort of carry vectors along with me as I travel. And if I have that, then I don't need to just do it with the vector that is pointing in that direction. I mean, imagine that I'm walking around in space carrying a gyroscope, okay? Just good old ordinary Euclidean space. If I have a gyroscope, and you might know if you sort of suspend a gyroscope so that you're not forcing it in some direction, you can just carry it around, and the gyroscope, if it's spinning, will keep pointing in the same direction. So this is a notion called parallel transport of vectors. It's just a way of saying you have some vectors, keep them parallel to what they were as you carry them around. Keep vectors parallel to what they were. And this notion that you keep walking in the same direction is, in the lingo of general relativity, you parallel transport your velocity vector. So you have a velocity vector, and you're also had this notion of how to move things, keeping them parallel to each other. And a straight line is one in which, if you have a vector pointing in the direction you're moving, you keep parallel transporting that. The vector that is your actual velocity matches what you get by doing your original velocity and just keeping it parallel. This is what math is all about. Let me just sort of pause to emphasize this. I just said what a straight line was in two different ways, and we all know what a straight line is. Like, it's this perfectly obvious thing. So why are we complicating it? Like, that's like the worst definition of a straight line you've ever heard. Invent a notion of keeping vectors parallel as you move, and then compare a parallel transported vector to your velocity vector and make sure they line up with each other. That is a definition of a straight line, but it seems a horribly complicated one. Why it will be important, of course, is because situations are more general than just flat space. We want to have more powerful. We're going to need that extra freedom a little bit, okay? So once you have that, you can parallel transport any vector. So let me imagine I have a different vector. So let's imagine at this point I had a vector pointing in a completely different direction. Okay, then the notion, the idea that I have a way of telling what it means to keep a vector parallel means that as I walk along this path, I can parallel transport the vector with me. I can construct a new set of vectors by just moving in that direction, keeping the original vector parallel to what it was. So I keep any vector, any set of vectors, parallel to what they were as I move along in space, okay? The velocity vector, the vector that tells me the direction I'm moving in, is the one that I use to define straight lines, but this is another equally good, this is something I can do once I've invented that capacity. And the reason why I'm telling you this is because it gives us a way of telling whether or not a space is curved that is as powerful as we're going to get, as powerful as we're going to need. Because here's the point. What if I start, let's do the sphere again. I'll just draw it again. I keep drawing the sphere, but that's for good reason. So here's a sphere, okay. And here is the North Pole, and here are 2 points, once again, on the equator, here and here. So we know what the great circles look like. These are the equivalent of straight lines. By the way, the technical term for straight lines in a curved geometry is a geodesic. I'm going to try not to use that jargon, but if you ever hear it, that's what it means. And so what if I have a vector that I will parallel transport? So I'll make it a different color once again. So here I have a vector, and it's initially pointing in that direction I'm going to move when I walk to the north. So I parallel transport the vector. So basically I just keep it as parallel as I can. There it is. Let me move this away a little bit so you can see it better. And then, but then I want to say, okay, but now let me do the same thing, but let me parallel transport along this path along the equator. So I start with the vector and I move it this way. And what will happen is, by parallel transporting it, it's not my velocity, it's just a vector I'm carrying along. By parallel transporting it, it will always remain perpendicular to the direction that the equator is in. Parallel transport has the nice properties that if two vectors start perpendicular, they always remain perpendicular as you move them. So I parallel transport it along, so here's the first path, and now this second path. I move along the equator. And now, let me keep moving this second path, so I now parallel transport it upward. So I take the vector that I have moved along the equator, and now I move it up to the North Pole. And what do I find? I find that when I get to the North Pole, even though in both cases, on the orange curve and the yellow curve, I've been parallel transporting a vector everywhere I've gone, I've ended up with two different vectors. The vector that I ended up with on the short distance orange path is different than the vector I end up with on the longer distance out of the way yellow path. Why? Because the sphere is curved. On a flat plane, that would not have happened. On a flat plane, if I parallel transport something on any curve I want, so here's a flat plane, I can take a vector, here's a vector, and I take some path, no matter how complicated it is, and I parallel transport the vector. Well, no problems, just remains pointing in the same direction the whole way. If I parallel transport it along a different path, like that, I can ask what happens there. The answer is the same kind of thing, and I will end up with the same vector. So this is yet another characterization of a way in which curvature shows up in geometry. We said that it showed up because angles inside triangles were different. It shows up because the relationship of the radius of a circle to its circumference is different. It also shows up in the way that vectors change when you parallel transport them. Okay? If you're in a flat space, they don't change at all. If you're in a curved space, they change a lot. This is a reflection of the fact that if you're in a curved space, there's no way of saying when you have two vectors at different points in space, or different points on the manifold, different points in space-time, whatever you want to say, two separated vectors, there's no unique way of saying, are they the same, or are they parallel, okay? That is not a well-defined notion, because to compare them, you have to move them next to each other, and moving them next to each other is the best you can do is to parallel transport it. And that was going to depend on the path you take to parallel transport it. So when someone says, for example, when cosmologists say a distant galaxy has a velocity of so and so many kilometers per second, they're kind of lying to you. At least they're being casual with the truth. What they're saying is that there's a redshift of the photons coming from that galaxy, which is equivalent to, analogous to, having a certain velocity. But there's no absolutely, in general relativity, well-defined velocity between two things at different points in space because there's no way of comparing them. And this is why if you go far enough away in an expanding universe, you will find objects that have an apparent velocity greater than the speed of light. And you will say to yourself, wait a minute, relativity told me that they can't have velocities greater than the speed of light. The answer is it's not a velocity. It's just an apparent kind of thing that is analogous to a velocity, and the analogy breaks down when you're too far away. Okay. So this is a little bit of abstract nonsense, but it gets us something important, that parallel transporting a vector is a way of defining straight lines and a way of characterizing the deviation from curvature. The problem with the pictures I've drawn here is, of course, these lines, these curves that I parallel transported around are big, right? They're long, they're finite sized, and what I want is something that will characterize the curvature at every point in space. So what we want to do the calculus thing. We want to shrink everything down to infinitesimally small, but also these curves I've drawn are kind of, arbitrary and random, right? We want a way to sort of systematize the curves we're drawing. So here's what we end up doing in Riemannian geometry to characterize the amount of curvature at one point in space. We say I define a loop around which you're going to parallel transport a vector, but it's an infinitesimally tiny loop. So a loop is just an arbitrary thing that would require an infinite amount of information to tell you the location of every point on the loop. What I want to do instead is say, here's a vector, call it v1, and here's another vector, v2. I'm going to define an infinitesimally tiny parallelogram by saying move in the direction of v1, then move in the direction of v2, then move back in the direction of v1 again. So my curve is go this way, go that way, go back that way, and then come back to where I started. Okay? This might make you a little bit uneasy because how do I define a parallelogram if space is curved and everything? The answer is, as long as I am infinitesimally small, this all makes sense. There's a way to make this completely rigorous using derivatives instead of finite-sized vectors, but it can be done. The point is, I define a loop in space-time not by giving you some arbitrarily weird curve, but just by giving you two vectors. I say there's v1, v2, and I make a loop by saying go down v1, then v2, then back along v1, back along v2. I come back to where I started. And what I do along the way is I will take a vector, and I will parallel transport it. So here's my vector. Let's call it v3. And I'm going to parallel transport it. So I'm going to keep it as parallel as I can. First along v1, then along v2, then back along v1, and then back along v2. And what I end up with is that it has changed. v3 has moved to a slightly different value. That is to say, v3 itself hasn't moved. When I parallel transport around the loop, just like in this sphere up here, I get a different answer. So in the sphere, I went along two different paths to get from one point to a different point, but I could have just gone along one path that was a closed loop equally well. So what that does, and this is the payoff here, that defines a fourth vector, v4. Oops. To be consistent, that should be a lowercase index, right? So what I get by starting with v1 and v2 and defining a little loop, and being given v3 and parallel transporting v3 around that loop, is a fourth vector, v4, which says by how much did the original vector change when I went around that loop. And I do all of this in a very, very infinitesimally tiny region of space, so I do it at every single point, basically. And I only need to know what's happening in the infinitesimally small location of that point. So what I get at the end of the day is the following piece of information. I get a map from three vectors, v1 and v2, which defined the loop around which I went, and v3, which defined the vector that I was parallel transporting, into one vector, v4, which tells me by how much did v3 change, okay? So this thing, remember I told you like way back when that all of math is just talking about maps between different spaces, okay? This is a map. This is, Mr. Riemann says you have a map from three vectors to one vector. This is like a little machine. At every point, it's a black box that says if you give me these three vectors, I'm going to spit out a fourth vector. And we have a name for this machine. This is called the Riemann curvature tensor. And again, no one's going to tell you this until you take general relativity or you listen to these videos. So a tensor is a generalization of the idea of a vector. You know, a vector is a set of components. A tensor is a bigger collection of numbers arranged either in columns or rows or matrices or cubes or something like that. But it's a whole big kind of set of numbers that can tell you a map from a set of vectors to another set of vectors. That's all it is. It's a way of mapping vectors to vectors. And the Riemann curvature tensor is this particular map. So the Riemann curvature tensor specifies at every point you can do this. You give me a point, I'm going to give you two different vectors, I'm going to parallel transport around a third vector and see how much it moves by. That's the value of the Riemann curvature tensor at that point. And it's a lot of information because you have to give me that value of V4 for every possible value of V1, V2, V3, right? Now, happily, everything is vectors, so you only have to give me some basis vector information. I can figure out the rest for myself. Every vector is a certain linear combination of basis vectors. So there's a finite amount of information you have to give me at every point, and Professor Riemann tells us this is a tensor that describes the total amount of curvature at every point in space. Okay. So this seems like a lot of work, right? This seems like we're doing a lot of work, and we are doing a lot of work. And if I were to attach all the mathematical, formalism to this way of doing things, it would be considerable. It would go on, but it's worth it. And the Riemann curvature tensor is exactly what is used in general relativity to characterize the curvature of space-time. Okay. But so again, usually in pop physics treatments, we don't go through quite this much detail, and we don't tell you about parallel transport, and we don't tell you about the Riemann curvature tensor. Let me reveal why it's worth trying to do it, okay? This information, what I'm doing is deriving, let's go back up here. What I did here for the shortest distance definition of a straight line is saying, you need to give me some data. You need to give me some information about the manifold whose curvature you want to know. And I can figure out what the curvature is on the basis of that data. What is the data in this way of thinking? It is the metric. It is the way of calculating a distance along a little tiny infinitesimal path that I could add up along a longer path to get the distance along any path, and then I can figure out what a straight line means. And from that information, what you can show is you can also calculate areas and volumes and what it means to be perpendicular and a whole bunch of different things. The metric tensor field is the fundamental thing in general relativity, is the thing that is the equivalent of the electromagnetic field or whatever. It's the starting point for doing general relativity. But then I gave you a whole other way of doing it, saying that we could think about curvature and straight lines and deviations therefrom based on this idea of keep walking in the same direction, keep things parallel transported. And if you notice in this page that I'm showing you right now on the screen, there's no distances. The idea of a distance didn't appear anywhere. I didn't need to tell you what the distance was or how to calculate it. How is that even possible? If the whole foundation of geometry was this metric thing which told me the distance, how do I get another way of calculating the curvature without even mentioning what the distance is? So the answer is that I needed to give you some data once again. I needed to give you data that revealed the answer to the question, what does it mean to parallel transport vectors? How do I know how to keep a vector constant as I move it along a path? And what that means is, in other words, parallel transport from one point to another is a way of basically, this is some curved manifold. I have point A, point B. I have some path that I move on, then some vector that I'm going to parallel transport along the path. Parallel transport is a way of comparing vectors at different points in space. So if you like, it's a way of connecting what's going on at one point in space to another. So it requires data or information, an answer to the question, what does it mean to keep things parallel, in the form of a connection, which is a field. Just like the metric, which tells me what is the distance along an infinitesimal path, the metric exists at every point. It's a field that can take on different values. The connection is the answer to how do I parallel transport vectors, and it is also a field. So at every point, I have a way of parallel transporting vectors in every direction. So it's a complicated mathematical object, and I call that a connection. If you just want to think about what do you mean by a connection, it's a field that tells me how to parallel transport things. It conveys that information. What does it mean to keep things constant, to keep things parallel along a path where I parallel transport them, okay? And the way that Riemannian geometry works is the connection defines the curvature. So I have a way of parallel transporting things, and I define the Riemann curvature tensor in terms of the result of that parallel transport. So the curvature of space-time or of any other space that you have is a function of the connection. Now, it turns out, as I said, that these two notions of straight lines, keep the vector parallel and minimize the distance along the path, are the same. They're equivalent to each other. You can match them right up to each other. So what that means slightly more formally is the metric defines a connection. And this is the way that Riemannian geometry works. The metric, which is telling me the distance between two different points anywhere, is secretly, and again, I'm not going into all the details, but provides a way for me to define what it means to keep vectors parallel as I move them. And that's the piece of information I need to figure out what the curvature is. So this is the missing step that they don't usually tell you about. They might tell you about the metric and distances, and they'll tell you about curvature, but in between there is the connection. And the reason why I'm emphasizing it is because we will see contexts in which there's no such thing as a metric. There's only a connection and only a curvature. So the metric is a special thing in general relativity, and the reason why is because the vectors you're moving are literally vectors pointing in some direction in space-time. Once we get to field theory, once we get to, in fact, what are called gauge theories in particle physics, we're going to be parallel transporting vectors that are much more abstract senses of the notion of the word vector. So like quark vectors that don't point in any region, any direction of space, but they point in color space, the space of quark colors, red, green, blue, things like that. And all this machinery of geometry, connections, parallel transport, curvature, etc., is still there in gauge theories of particle physics, even though the metric is not there. So I'm sort of killing two birds with one stone. It's an incredibly complicated, abstract stone, but nevertheless, okay, that's how it works. It's worth doing it, I think. Good. I think that's all we need about geometry now. So I remember I'm trying to repeat myself because they are hard concepts, honestly. Like, I get it. This is what we're trying to get. We're trying to say that this notion of parallel transport lets us define the curvature at any point in space. We can relate it to this other notion we had of the metric, and it all fits together in a nice geometric bundle. In fact, when we thought about Newtonian physics versus the principle of least action, the Newtonian Laplacian way of thinking about the laws of physics was start with a point and just chug forward using F equals ma. You get the same answers doing things that way as you do with the principle of least action, which says take the whole path and minimize the action along the path. You might think, is this analogous to these two different ways of defining straight lines? The whole path and find the minimum length, or parallel transport your direction, your momentum vector? And the answer is yes. They are 100% completely analogous. It's the differential version versus the integral version, if you want to think about it that way. Okay. So that's geometry for you. There it is. That's all you need to know. Everything else is derived from that in some sense, but the derivations might be hard. Next, we're on to topology.